Alright guys, well here's a new type of function that we have not seen thus far, in this class at least. So if you take a look at those points there, plotted a few points, got a little graph going, we should note that the point 0, 0 is also on there. That's a kind of an important point, right? That's the intercept. Do we notice anything about those numbers, how the x's and y's relate to each other? If I add another point on here, this point here would have an x value of 16 and the y value there is 4. So hopefully you're recognizing the fact that this is actually deals with square roots, right? If you take a look at the y value, and check this with all the points, isn't the y coordinate equal to the square root of the x coordinate, right? It goes through 1, 1, the square root of 1 is 1. It goes through 4, 2, the square root of 4 is 2. Okay, 9, square root of 9 is 3, and so on. So this actually is a square root function, and that's what it looks like. It actually starts right here. Okay, it doesn't go on forever like the lines we've seen in parabolas where it had a domain of all real numbers. This one does not go through all x values, okay, or all y values for that matter. So the domain on this one, if you take a look, it's starting at 0 and then going to the right, on and on and on. So the domain could be written as any x value as long as it's greater than or equal to 0. Okay, or you might see it as interval notation, meaning it's going from 0 to infinity. Okay, that's called interval notation. We use the bracket there because 0 is actually included, but you can never equal infinity, so we use a parenthesis to say it just goes to infinity but does not include infinity. And then the range for this one, if you take a look, y values, same kind of thing. There's a minimum y value at 0, and it's going to go up and up and up. Okay, it's growing slowly in the y direction, but it's still technically growing. Okay, and if you think about the equation, y equals the square root of x up here, if you think about what we learned, when you take the square root of something, the thing you're taking the square root of right here must be greater than or equal to 0. Otherwise, you'll get like an imaginary answer out of it. You won't get a real number answer out. That's why the domain states that x must be greater than or equal to 0. And as far as the range, the y over here, when you do take the square root of a number, like you throw a square root of 10 in a calculator or something, it's going to give you a positive output. Okay, that's why when we solve equations, we have to include the plus or minus in front of it to include that negative value as well. But that's why the domain and range are both all numbers greater than or equal to 0. All right, so this function, this is known as the parent function here. This is just the plain old regular basic y equals square root of x. And if you remember, with other functions, I think we did absolute values, and then we did this with quadratics as well. They can be transformed, right? They can be stretched or shifted or reflected or that kind of thing. So the same kind of rules apply. So let's do as a quick review, as a recall. I think the first one we did was absolute value functions way back in the beginning of the year. So the same properties and whatnot apply. So if this is the basic function, just the absolute value of x, how would each of these compare? What transformations would occur? Okay, so if you think about the first one, if you're multiplying by 2 on the outside, that's going to be what's known as a vertical stretch. Remember, that would kind of just raise the y values. In this case, it would double them, and it would look like the graph has been stretched in the vertical direction. With part B, we're multiplying by 2, but that one is considered inside the function, right? The function was absolute value, so when you multiply inside, when you do anything inside, it affects the x direction. So it's going to be a horizontal transformation, but in this case, just remember that anything inside is the opposite effect. So instead of this one stretching, this is going to actually be a shrink. And what it might do, just to kind of visualize what's going on there, if the parent function for this one, again, is a nice absolute value, looks like that. What a horizontal shrink would do, all the points would actually kind of get closer together. They'd be compressed in a little bit more, and it would look like it's kind of squeezed in horizontally. Okay, the other options, if you had a plus 2 inside the function, again, it's inside, so it's going to be a horizontal, or it's going to be an x transformation. Opposite direction though, right? So since this is plus, it would actually shift a positive is typically to the right, but in this case, since it's inside, we're going to do the opposite, right? This thing would shift 2 units to the left. Okay, and then the last one out there, we have a +2 on the outside. Anything on the outside affects y values, and we do what it says. So it would actually shift up, is not the opposite. So this thing would shift up 2 units. All points would shift up. It would have the same shape. It would look like a V, just kind of slid or translated is the fancy word there. All right, so let's think about these in relationship to our square root function. So I have graphed here the basic parent function that we saw at the beginning. And let's just kind of think about what would happen if we had a y equals the square root of x with a -3 on the inside. Okay, so again, anything on the inside is affecting x directions, and it's going to be the opposite. So a -3 is actually going to shift to the right. And here's what I would suggest doing. Just take a couple points from the parent function and just shift each of those 3 units to the right. So that first point would go 1, 2, 3 would be here. That second point, 1, 2, 3 would be here. Then the next point, 1, 2, 3. So it would actually be doing just like this kind of thing. It would shift everything to the right. And let's talk about the domain and range of the new transformed function. Okay, if we take a look, this thing now starts, its x value started at 3. So the domain of this thing could be written as all x values greater than or equal to 3. Okay, or using that interval notation again, it would be from 3 to infinity. While the range, take a look where it starts, the y values didn't change, right? The y values are still starting at 0 and going up from there. Okay, so from 0 to infinity. Okay, let's take a look at the other one now. The green, the y equals the square root of x, and then there's a +3 on the outside. Okay, so we would take the same 3 points, that original starting point, which was here, would move up 1, 2, 3 units. This point would move up 1, 2, 3 units. This point would move up 1, 2, 3 units. Okay, and basically every single point's going to move up 3 units. The shape's going to stay the same. It just was a vertical translation. So in this case, let's think about where does this graph start at. In terms of x values, it's still at 0 and going greater than or equal to 0. Okay, again, interval notation would be the bracket from 0 to infinity. But the range has changed. Okay, this one starts out, its y value is always greater than or equal to 3. Okay, because the vertical shift in there shifted the range up a little bit. All right, some other transformations. What if we had, and again, here the parent function's graphed. Okay, so I'm just going to plot a couple points that we can use as our reference points. And that thing does keep going. The blue one, 2 times the square root of x. So that's a multiplier on the outside. That's going to change the y values. They're going to become doubled. Okay, so if we think about the first point, its y value right here is 0. Even if I times that by 2, it's still 0. Okay, this point, y value was 1. If I double it, it becomes 2. This one's y value was 2. If I double that, it becomes 4. Okay, let's just do one more. This point here had a y value of 3. It's now going to be 6. Okay, so we can kind of see, hopefully, the vertical stretching going on. This thing is just like taller, vertical stretch. The domain and range did not change. Okay, it's still starting at 0, 0, and both x and y are just going to infinity. It's just kind of getting there faster, but the domain and range would not change on that one. All right, for this one now, we have a negative on the outside. That's just the saying -1 times the square root of x. So we're going to take each of the x values, and the y coordinates, and times them by -1. So that one's going to stay there. This point that was here is now -1. This point would now become -2. This point would now become -3, so down here. So what this does, when you get a negative multiplier, that's actually a reflection. Okay, and it's a reflection over the x-axis. Okay, because again, it was outside the function, so it's impacting y values. It's making the y values negative, which is reflecting over the x-axis. Okay, domain and range on the green one of them has changed. Okay, the domain, if you think about this thing, it's still here and then it's going to the right. So its x values are still always greater than or equal to 0. Okay, but the range, look at the y values. It's starting here. That is a maximum now, and it's going down from there. So the y values are always less than or equal to 0. Okay, and to write that as an interval, we would say that it goes from the minimum it could be, it goes all the way down to negative infinity, all the way up to 0, and it does include 0. Okay, so the range changed on that one. All right, now last one, if we had a negative multiplier on the inside, okay, what that's going to do, anything inside the function impacts x values, so all the x values are going to be getting flipped. So the 0, 0 is not going anywhere, but this point right here is now going to flip over here. Okay, this point right here, 1, 2, 3, would now be over here. Okay, this is a reflection as well, but this is actually going to be a reflection over the y-axis. Okay, because again, anything inside the function affects the x values. So in this case, our domain and range. The domain of the new graph, take a look, it's going from a negative infinity up to 0. Okay, the x values are always less than or equal to 0. So the minimum it could be is negative infinity. The maximum the x could be is 0. And then the range is still the same. The range is still 0 and up. So the range is still from 0 to infinity. Okay, here, this is just kind of, I know it's kind of hard to look at a lot of stuff going on, but if you just glance at it for a second, you can see there are different graphs, just a whole bunch of different transformations all on the same page. Again, it's kind of hard to see. Maybe just pay attention to, let's focus in on one. Let's look at this one, for example. Okay, I'm going to try to highlight that one for us. That one is the one that is right here. Okay, and just kind of notice that one shows two different transformations. It did have the +1 on the inside. That's why it's starting out. It looks like it's starting out in the middle of nowhere. So when you graph these, make sure you're accurate with the starting point. The +1 in there shifted the graph to the left one, and the +3 out here did shift the graph up 3. So it actually does start out like in the middle of quadrant 2. And that's just where it starts. So for that one, for domain and range, just to kind of see one more example, the domain, it's starting at -1 and then going on and on and on. So all x values must be greater than or equal to -1. While the range, the y values start at 3 and then go up and up and up. So the y values must be greater than or equal to 3. Okay, so you can have more than one transformation. If you're typing this into a calculator or Desmos or something to help you graph it, make sure that you get out of the square root when you want to. Okay, meaning that +3 you need to arrow over so it's not under the square root. Because if it were under the square root, it would get combined with the +1 and it would make it a x + 4, and that would not be the same graph. Okay, so that's kind of graphing square root functions with their transformations.